Hi there, guys. Welcome to my first chemistry video. And I decided to make this video on balancing chemical reactions because one of my students is in chem at the moment and he had trouble with the concept. If you're learning it for the first time, it's pretty tricky. So I wanted to make a video kind of explaining how the process works. So this video assumes that you have prior knowledge about chemical reactions, the different kinds and how they work. I highly recommend you brush up on the prerequisite material if it's been a while since you've seen this stuff, because it does depend heavily on knowledge of chemical reactions and how they work. So let's dive right into let's talk about what it really means to balance a chemical equation. So we want to make sure that we have the same quantity of every atom on both sides of this reaction sign. So let's take a look at what appears to the left. Everything to the left of the sign, we call those our reactants. Everything to the right of the sign, we call those our products. So let's take a look at the reactants. We have H2O, we have a water molecule. So what I like to do in my head is I just like to count the number of each atom. So we have H2, that would be 2 hydrogen atoms. We only have 1 oxygen though. Let's take a look at what we have on the right side in our products. So it looks like we have just 1 hydrogen and just 1 oxygen. And we can tell this one's not balanced because we have a different number of hydrogens on both sides of the equation. So we have 2 hydrogens on the left and 1 hydrogen on the right. We need to make sure that we have equal numbers of each on both sides of the equation. So the question to ask yourself would be, well, how do we change this hydrogen? How do we change the quantity of hydrogen so that we have 2 just like we have on the left side? So this one is pretty straightforward. I picked this one just because I thought it was really easy and it helps me. It would just, I can't talk today, I'm tongue-tied. It would make a nice example to help us really understand what's going on at the base level. And that's why I chose a really simple problem to kind of just introduce us to this topic. So we have 2 hydrogens, 1 oxygen, and then on the other side, we have 1 of each. So like I said, we want to make sure that we have not 1 hydrogen on the right, but we want to turn this into 2 hydrogens. So this one is pretty straightforward. But by the way, before we continue, I just want to let you guys know that we can't ever change this subscript. If we change that, it completely alters the chemical makeup of this, and that's something that we can't do. The only changes we're able to make in this process would be the coefficients. We can only change or add or remove coefficients. We probably won't be removing any coefficients, but we will be adding our own and we'll be changing some of them. So let's see here. So the O is already balanced. We don't need to worry about that. We want to make sure that we have 2 hydrogen atoms instead of just 1. So I'm going to just put a coefficient of 2 right there. And I'm going to change the number of hydrogens over on the right side of our equation to 2. So we have 2 hydrogens and 1 oxygen on the left, and we have 2 hydrogens and 1 oxygen on the right. So we know we are 100% balanced. We're good to go. We're finished with this one. Let's try maybe a bit of a more complicated one. Let's say we have a molecule of dinitrogen reacting with a molecule of hydrogen, and they produce a 1 molecule of ammonia. So I want to do just like what I did in the last example. I want to just write down the quantities of everything I have. So on the left side in our reactants, we have 2 atoms of nitrogen, and we have 2, sorry, I'm tongue-tied today for some reason. I don't know why. Usually this doesn't happen. I apologize. So we have 2 nitrogens. We have 2 hydrogens as well on the left. And then on the right, we have 1 nitrogen, and we have 3 hydrogen atoms. So nothing is balanced. We have different numbers of hydrogens on, no, sorry, we have different numbers of nitrogen is what I meant to say. We have 2 nitrogens on the left, 1 nitrogen on the right, that needs to be balanced. And then we have 2 hydrogens on the left and 3 hydrogens on the right, so that also needs to be balanced. This one is a bit more involved. We're gonna have to do maybe a few more steps than what we did last time. It's gonna be a bit more complicated. And we call this a synthesis reaction. Whenever we have dinitrogen reacting with hydrogen to produce ammonia, we just call this a synthesis reaction, or synthesis reaction is what I meant to say. So let's go ahead and see if we can balance this. So a good strategy is to always start with the most complicated looking thing. And I'll show you exactly why in just a second. I want to move this over. I want to give myself enough room to write the coefficient. Perfect. So it's always a good idea to start with the most complicated thing, because if you start with a simple thing, if we do something like that, for example, we have 4 nitrogens now because we have a coefficient of 2 and we have a subscript. So in a situation like this, I feel like I should just kind of go over this part real quick. So in a situation like this, wherever we have a coefficient and we have a subscript, the total number of atoms in this particular term is just going to be the product of the subscript and the coefficient. So we get 2 times 2 is 4. So this side has 4 nitrogens. So let's talk about what happens if we start with the simpler things instead of the more complicated things. So if we slap a 2 in front of there, we now have 4 nitrogens. So we're going to have to put 4 out front of this nitrogen as well, which means that not only are we changing the nitrogen, we're changing the entire atom. So this H3 is also being affected by nitrogen. So we have 4 nitrogens on the right, and now we have 4 H3s as well, which means that we would have a total of 12 hydrogen atoms. So we already have 2 on the left. We want to figure out what the coefficient should be to have 12 hydrogens as well on the left side. So we want to just ask ourselves, well, 2 times what number gets us 12? That would be 6. So this one is balanced, but we're not done yet. There is another way we could do it. Sorry, I can't talk today. We are not quite finished yet. It isn't in simplest form. We have to reduce this to a simpler form in the same way we would reduce a fraction. In the same way how 2 over 4 is reduced to 1/2, because 2 and 4 have a GCF, a greatest common factor of 2. And whenever 2 numbers have a GCF that's not 1, you can always reduce the fraction to some capacity. So let's take a look at our coefficients. So we have a coefficient of 2 and 6 and 4. So 2, 6, and 4 all have a greatest common factor of 2, which means that we can just divide all of our coefficients by 2 and get a simpler form of the same reaction. This turns into 2 ammonia atoms. So let's just verify that we did this right. Let's count everything. So we have 2 nitrogens on the left. Look, we have 2 nitrogens on the right too. Cool. On the left, we have 6 hydrogens, and we have 6 hydrogens on the right as well. So not too bad. It's a bit more complicated than the last one, but I felt like this was another really good example to kind of understand how the process works, just to practice it a little bit so you have a good idea of how to tackle it and what a good place to start might be. So it might have been a little bit faster to start with the more complicated one. We could have saved a little bit of time by starting with a more complicated one, because if we swap a number 2 in front of there, it could be any number, but if we swap a coefficient in front of this molecule, it affects everything. And it tells us directly that not only is the nitrogen going to change, but it's also going to affect this hydrogen as well. And because when you put a coefficient in front of a molecule like this, it affects multiple things. If you put it in front of just a single element like this, we have dinitrogen, it only affects this. So we want to start by putting coefficients in places where it affects everything, because it's much easier to correct in a situation like this than it is to start small and work our way to the more complex. All right, let's try another one. So this is going to be a double replacement reaction. Let's say we have carbon dioxide reacting with water to produce glucose and a dioxygen molecule. So let's take a quick look at the counts and see how many of each element we have on both sides, how many of each atom. So if we look at the left, we have 1 carbon. We have 2 oxygens right here, another oxygen right there. So we have a total of 3 oxygens on the left. And we have 2 hydrogens on the left. Notice how we have 1 molecule that's affected by all 3 of those elements. So we're going to start with this one. We want to make whatever change is necessary to this glucose molecule so that we have the same number of every atom on both sides of the equation. So we have 12 hydrogens. I like to start with the biggest number and then figure out how we want to respond to this on the other side. So we have 12 hydrogens. If we go to the other side, you can see that we have 2. So we want to do what we did last time. We want to try to be strategic about what the coefficient should be for this water molecule. So we can tell that we have 2 already. So the question we want to ask ourselves is 2 times what number gets us 12? That would be 6. So that has to be the coefficient for a water molecule. Otherwise, we won't have a balanced amount of hydrogen on both sides. So now we have 12 hydrogens, but the thing is the 6 doesn't only affect the hydrogen, it also affects that oxygen as well. So let's do a recount, see how many oxygens we have on the left. So on the left, we have 2 oxygens, and then we have 6 more oxygens. So we have a total of 8 oxygens on the left. Let's see what we have on the right. Hey, look, we have 8 oxygens on the right as well. Perfect. So it looks like the oxygens are balanced already. Looks like the hydrogens are balanced. Let's see if the carbons are balanced. Doesn't look like they are. We have 6 carbons right here. We only have 1 carbon on the left side. So we want to put a coefficient in front of our carbon dioxide molecule to make sure that we have the same number of carbons on the left as we do on the right. So on the left, on the right, we can see that we have 6 of these. So we're going to have to multiply the entire molecule by 6 to have the same number of carbons. But notice how it doesn't only affect the carbon. This coefficient of 6 also affects the oxygen. It changes the number of oxygens we have. So let's see how many we have now. So we have, this would be 6 times 2 gets us 12. So we have 12 oxygen atoms in our first reactant. We have 6 oxygen atoms in our second reactant. So that brings us to a total of 18 oxygens. We want to make a change to this so that we also have 18 oxygen atoms on the right side as well. We always want to make sure we have the same amount. So let's count how many we have already. So it looks like we still have 8 from before. So to get a total of, what did we want to get? 18. We want to get 18. So that means we're going to need to add 10 more oxygen atoms, which means that we don't want to change this at all, because if we change this at all, it makes things really, really messy. It affects all of these. Instead of changing the glucose atom, we'd rather just change this one, because if we put a coefficient on there, it only affects the oxygen. We don't have to worry about it affecting any other parts of the reaction. We don't have anything else to balance after that, which is really nice. So it's always in your best interest to start with the most complicated side, the most complicated product or reactant, and then from there, work your way down to the smaller bits like this O2 atom. So we wanted to make this into a 10. We want to make sure that this part of the equation is 10 oxygen atoms. So we want to ask ourselves, what number do we have to multiply 2 by to get 10? That would be 5. So it looks like this is balanced, but let's just verify real quick and do a quick count of everything. So on the left, we have 6 carbons. On the right, we have 6 carbons. So far, so good. On the left, we have 12 plus 6 oxygens. We have 18 oxygens on the left. And then on the right, we have 10 plus, oh, I think I did something wrong there. We have, here, let me erase this coefficient. I think I messed up. Sorry. I want to do a recount of the oxygen. So we have 12 oxygen, and then we have 6 more. So we have 18 oxygens on the left. And then on the right, we have 6 plus 2 more. We actually have 8. So we want to make whatever change is necessary in order to, actually, you know what? I'm getting ahead of myself. Give me a second. Sorry about that. I got mixed up a bit there. So we do want to have a coefficient in front of this product, this part of the product, and it's going to have to be something other than 5, because if it's 5, we only get a total of 16 oxygens on the right. What we really want to have is 18. So this is actually going to have to be a 6, because now if we have 6 oxygens right here, now actually we have 12 right here, 6 right here, so we have a total of 18 oxygens on the right and on the left. Sorry about that, just got kind of mixed up. And to be honest, I'm not trying to make excuses for myself, but it's been a really long time since I took chemistry myself. Been a while since I've seen this, so I apologize if this isn't up to my usual quality, but this is completely balanced. We have the same number of all of the atoms on both sides of the equation. Life is good.